Hello, my name is Rob Hirschfeld. I'm CEO and co-founder of RackN, and this is a story about our journey through 12 years of generations of our product and our software, and it's currently in production use at data centers powering actually well over 10,000 instances in production environments now. But how we got there is an exciting, challenging, and sometimes scary story. And what I want to do is frame it out a little bit and then go back through and tell you some of the stories that were pivotal in that journey. And it starts from an open source project that we started at Dell. Some of you might have actually heard of it, called Crowbar. It was the first OpenStack installer. We had a generation of that called Open Crowbar, and then now we promote that as Digital Rebar. It's actually a product, and that's an important distinction in how this progresses. And what you'll see over time is in that first generation, we really built something that was an MVP. It's based on Chef. I'll talk about a lot of these details as we go. When we went through that process, we did a real second system, if you're familiar with this paradigm. When you build one system, you go to redesign it. You put in all the things that you're supposed to put in that you forgot the first time, and you design it in this way over complex. And that caused us to have this problem. The second generation of the system actually scaled worse. And so we had to throw it out, start over, and I'm going to walk you through that journey and sort of how that evolved. And the reason I'm telling you this is that these are very real problems, right? These are things that you are going to find as you go through your own operational journey to try and improve your scaling and your automation. Because we see people building the same thing over and over again. And what we've seen is, once we got the architecture right, we've been able to add features, incrementally grow the system in a very clear way. So not only do we improve the scale of the system, but we did it while we added key missing features. And that's the indication of success in a what's now a fourth generation architecture. But this is the scary part. During that re-architecture, we had to reset everything. Right? We had to reset customers. We had to reevaluate how everything was done. And when you go through this process, you have to have the political cover, the capital, whether it's financial capital, political capital, operational team capital, to weather that type of a change. So no matter how good the reasons are I'm going to show you, you have to remember that RackN had an existential crisis in getting through that transition point and actually improving. And what we see happen is a lot of companies build into this first and second generation and never make it out to that third generation. So before I explain and tell the stories about this re-architecture, and I'm going to match the architectural tech change with stories for you, it's worth understanding what we do. Right? RackN is an infrastructure as code platform that addresses this sort of fundamental need around infrastructure as code, which is operations teams. The CIO says, I want you to be more like a dev team. I want the predictability. I want the CI/CD pipelines. I want things to be more governed. Because the challenge that we see in the industry is that we have good tools. Right? We have great people. I mean, the people I've been talking to here are amazing, fascinating stories. And they have good vendors. But the complexity and the challenge of making all that stuff work together is incredibly high. And the way I like to explain this to non-technical people is, imagine that we were building a house. We had electricians working in the bedroom using US plugs. We had electricians working in the living room doing European plugs. And we had electricians in the kitchen just wiring stuff together with wire screws. And then you put up the drywall, and the log4j bug happens, and nobody knows what's going to burn down. And so we have this very real challenge to be better at having repeatable processes. And that's really what we've been trying to do, turn operations work into productized work, where it's software and software deliverables and things like that. And you have to understand how that scales. And that's really relevant to understanding what we've been doing and why we went through 4 generations of work to do it. Ultimately, the goal for us was very simple. We wanted to have the same code at every customer. We want to be able to collaborate with our customers when we fix things and know that if we put automation back into the field, that our previous times of improving that automation could come back. Or if a customer found a bug, everybody could benefit. We wanted to work on toil across the industry. And that, to us, has been the goal all along. And it's a really significant thing. But what it requires us to do is really think about how we build the architecture. And I don't want to spend any time on the product plane. Please come by the booth if you want to understand more about how the product gets built. But I do include this because it's important to understand there's workflow components here, there's database components, there's multi-site components. All these things have to fit together to have the solution work. You don't get in operations, you all know this intuitively, it's worth expounding. You don't get to do things halfway. An MVP is not going to work, which brings me to my first story. So when we first built Crowbar, we built it on top of Chef, because Chef was already doing configuration management. That's the main thing that we needed to do. We added a Pixie boot component and started provisioning. And literally, we had a parallel database in Chef where we did a whole bunch of profiles and then tried to drive them. And what would happen is, to make this work as an MVP, we would do all the work in our lab. We'd box up the rack. We had a cute little case for it. And we'd ship it to the customer site. And my co-founder, CTO now, but chief architect at the time at Dell, would fly on an airplane and we would deliver the rack and Greg would show up on site at the same time. And what we found was every single time he did that work, he had to reinstall it from scratch. We could never anticipate what was going on the first time. And we always found that when we fixed something, the next time he did that, the person who we'd left the last rack with couldn't benefit from anything we learned. And that is a huge lesson in what you're building and how we're building this. Because if you want things to progress team to team to team, you have to be able to have code that every team can use if they choose to pick up those versions. So that was the first thing that we started working on. Along the lines of this, one of the things we were able to do is open source project in Crowbar days, and SUSE started using Crowbar as their OpenStack installer. And when we rewrote it, our second system problem, they said, nope, 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 too risky for us. We're going to stay with the old Crowbar. Years into this migration path, they actually found me at a conference and said, Rob, we need your help scaling Crowbar. And what I had to turn to them and say is like, you will never scale that MVP past about 200 machines, which is where they'd been getting. Because some architectures have a speed limit. There is an architectural speed of light. And you have to be aware of this when you're building things. If you build an MVP and you're like, this is just going to be great, there are times when you make an architectural decision, like depending on Chef and idempotency to resolve issues, that you will never overcome how fast or how big you can scale it. And you have to recognize when you're on an architecture that's running out of gas and abandon that architecture before you hit that situation. In this case, just to satisfy the technical people, to do Pixie booting, you have to drive DHCP and DNS. And if you are in a Chef loop, you can make the Chef like repeat every 5 minutes. But if you're bouncing your DHCP server and has to reload the whole configuration file to come back online, and that takes 5 minutes, you now have a collision. And so you literally have the update windows and the reset windows overlap, and that's as far as you can grow. So it completely ran out of gas. So we took all that work and we said, we know better what we need to do. We need to build a directed acyclic graph, a DAG, to drive our configuration. So we built this beautiful system that would figure out everything that needed to happen to scale the system better. Because we knew that if we could figure out all of the things that we had to do in advance and then drive that through, we would be able to get it done. There's some videos. I couldn't find the video source for you, but of us doing these beautiful multi-cloud Kubernetes deployments where you have this graph and it's literally flipping through all the things that need to get done. We built stored procedures and Postgres to make all that stuff happen. And I was using this slide in my presentations about the architecture. If you ever are using a jet engine to compare your architecture, you know you were in the wrong direction, right? This is one of the most complex machines ever made. And if your application, if your deployment technology requires you to digest that type of complexity, even if it's the reality and operations really is this complex, then you know that you are now in a zone where other people will not comprehend what you're doing to make operations happen. And that was one of the big lessons learned in this generation, is that as cool as it was, only 1 or 2 people on the planet could actually understand it and modify and grow it. And so we realized we were in this state where things were in very troubling. Right, we'd had this complexity. We were helping customers resolve and bake off and understand this. And we have this story. We'd been doing this version 2 work, the DAC and all those things I was telling you about. And we had gotten to a point where a customer had put it into a bake-off. And their goal was to be able to provision servers as fast as they possibly could. They had about 1,000 servers. At that time, it seemed like a lot. And they cared about every second that it took. They installed the first version of the product, the one with the DAG. And they booted the server. The system automatically identified that their BIOS was out of date, patched their BIOS, rebooted their system, then went back, did an OS install. It's beautiful software. Did all this cool stuff for them. And they called us up, and they said, you failed the bake-off. We said, but we installed the software. We patched the server. We did all this stuff. And they said, yeah, but we didn't expect that to happen. The thing that we were baking you off with just ignored all that and just installed the OS. And what we realized, and this was critical, is that there are times when doing unwanted operations are actually harmful. And it's even more harmful if you do unwanted operations in a way that don't tell people that they are doing unwanted operations. And so out of that experience, the first lesson was you actually have to have transparency baked into the system. It has to be predictable. You have to understand it. We were having a team lunch, team dinner. We just had a strategy meeting. Our CTO had been helping. This is Technicolor. I'm naming them since they're not a customer anymore, and it's been long enough. And they called us up, and they're like, yeah, you're going to fail the test. We'd been working on this little project, the rewrite project, beforehand. And CTO, we're at dinner. He says, hey, they're having trouble. Can I send in the new version of the software? And we're like, OK, no problem. He gets up from dinner. He goes, calls them up and says, all right, install the new version of software, right, disappears. About 15 minutes later, he comes back to the table. And we're like, oh, what happened? You know, were we out? He said, no, they installed it. They got it working. Everything's going, and we won the test. That was the moment we realized that version that we'd been babying along was dead. We literally sat down, and by the time dinner was over, we changed our business strategy. We knew we had to invest fully in that new product because it was so fast and easy for them to get started. And that always, the startup time, your ability to deliver and be repeatable is so essential in how these things work. Right? I'm doing a lot of talking lately about complexity and talking about complexity, and complexity is necessary and it's real and you can't make it go away. But at the same time, you have to understand when you're adding to the complexity problem and when you're managing the complexity problem. And that was a critical moment for us. And it really changed how we build the whole product, right? You can see in this graph, our complexity of the underlying infrastructure dropped off the cliff. I'm going to pause and talk for a second because there's a slide in here that is worth mentioning also. So along the same lines, and this will seem familiar to a lot of you because we're very excited about microservices. When we built this DAG version of the product, it had a database, it had a reverse proxy server, it had a Pixie server, a TFTP, DHCP. Like, we'd taken all of these components, broken them into microservices, built an auth system, put it all under Compose so you could bring up the system, because we knew, with the DAG doing all the work, that we would have to have the database go onto a dedicated server. All that work to figure out what we were supposed to do next had to go somewhere, had to be done in some part of the architecture. And when we put all that in one place, we knew we had to build this microservices architecture, and that actually created part of the complexity for the system. So in order to pre-scale and this is the lesson with this, in order to pre-scale the system, we broke it into microservices. And when we did that, the complexity of the system went higher. The actual performance of the whole system, its ability to carry the number of instances, plummeted. Because instead of doing one thing or having coordination only in one layer, we actually had made it required that we were constantly pinging back and forth. And every time we had any action, we had to do a security and an auth check, talk to a service to make sure the token was valid. So we'd added something that was really, really complex. And this is the way my CTO described it. He's like, you have to realize that we, in microservicing the system, right, we were designing for a 100,000 entity system. And his comment is, operations doesn't require us to do that. So another lesson that came into this in this series is that when you're dealing with operations, even if you have a huge operational footprint, most of your operational units are small. They are teams, they are racks, they are data centers, they are sites. And so your need to build something that can scale to 1 million entities, even if that's what your whole estate has, isn't necessarily your operational requirement for your software. So when we built the new system, what we actually did was we sat down and said, how do we build in the thousands as a scaling model? And that was a lot of how we rebuilt the system. As a matter of fact, the first database, we just used a file system, and I'll get to some of those pieces. Because here's what happened. We built this system where all of the components could interact within the same backend. So the short story is we converged our TFTP, our DHCP server, our HTTP server, our API, our data store. They became more tightly integrated, which allowed us to do a lot of things. It's Golang, so it's possible to have all the services baked into one thing. It's super, super handy. And that's relevant because the next big innovation we had in scaling was understanding that we didn't want the back end to do the work. So when we built the system and the way we looked at it, we said, you know what, we've got an API server that can store data, coordinate actions, but if it's doing the work, if it's an SSH server and pushing into the agents to do everything and we have to track all those processes or have to do a whole bunch long-running out-of-band management actions to make those things happen, we can't scale that. The back end becomes the bottleneck again, and we lived through that. So in the next version, and this was V3, what we actually did was we said, you know what, our CLI could actually become our agent. And what we did is we would boot a machine, we would start the CLI as an agent, and then it would pull all the work into it. It was actually doing the code execution. It was actually pulling in those processes and running it. The server would still figure out what the task list was, but the agent running on the systems would actually do all the work, send back tasks, and then get the next work. There's actually a fair bit of logic in that. But it was a remarkable thing for us to realize that we could start putting, just like we converged services together into our back end, the client actually could start having overlap in what it did. And today, that client has all sorts of embedded features. It includes JQ, because we need JQ everywhere. So we just bundle that into the Golang API, into the CLI. And that means that when we look at our utilities, it becomes much simpler to make sure that we have everything in place. The other thing we did with this was we gave up on the idea of needing a DAG. So what we realized was, even though there are times when you need to synchronize operations across a lot of different components, we don't have to have a DAG to do that. As a matter of fact, it was harmful to our operators. That it was much better to have a more linear flow and then use the back end to do coordination points and wait and figure out those incremental points than it was to try to let the server do all that computation. So this represented a real shift in our thinking from having a server that was going to do a whole bunch of logic for us to actually letting that come and be done on the clients and that more linear workflow process. And it's interesting because if looking back on this was a pivotal moment for us, and we've been slowly making the workflows more and more complex and adding more logic and chaining and things like that. So we started, and this is where it's really important, instead of in the last version where we had pre-solved all that stuff, we've been adding it back in, starting without it. And that was a huge mindset shift in how we thought about the architecture. And this is a challenge because you have to be nimble enough to add things back in, and you have to be able to stay ahead of it. But we were incredibly aggressive about not over-engineering. Right? And that's when I was reviewing this talk with our CTO, he's like, we stopped over-guessing. We stopped guessing. And that's been really important from an operational perspective. Our next big aha came as we were starting to get into more and more enterprise applications. So we had a banking customer who had a 30,000 machine HPC system. They called us in for a conference room pilot. They had 3 regions with 10,000 machines in it. They had a 2-hour window once a week to re-provision the machines. And they had to do that once a month. So every weekend, they would, you all know these stories, they would run 2,500 machines through the repeat cycle inside their 2-hour provisioning window. They had a 20% dropout rate, and it was taking 3 hours to do the process. So they called us in to say, we need help moving this faster. We have to get it fast. It has to be more reliable, and it has to go faster. And the thing that was interesting is, right, this is another Greg on an airplane, conference room pilot. I was there trying to run interference and keep let him do the work. And what happened here is that the ops team said, yeah, this is no problem. Here's the steps that we need to go through to get these things working. And through no lack of their own knowledge, they didn't know what actually was going on in their provisioning operations. And what we found was we thought was going to be a 1-day conference room pilot where they would come in, we would do their provisioning, get their Pixie, install their agent, and do this. It was an archaeological dig. And I'm sure you all have this experience, especially if you're going into systems that already work. And the bank wasn't wrong. This is really important to me. Our customers are never wrong in their operations. Everybody comes to us and says, we're doing it wrong. And they're like, no, you're doing it just like everybody else. The fact that they had 10 systems and they only knew about 3 of them that they had to integrate with to do an end-to-end workflow is not a fault of the team. It's a reality of what they are and the lack of integration that they just don't realize that they have to do it. And so part of this integration system was we had to go in and actually come through and archaeologically dig through each system that they had to go. And literally Greg had to do the integrations on the fly back in these early days to figure out each one of those systems and then code that integration in. And I tell that because it really influenced how we build the system, because we know when we show up at a customer or if somebody tries and downloads and uses the product, we'll have 9 out of their 10 integrations, maybe. We're getting to a point where that's pretty predictable, but there's always one that we don't. And so part of the design in any of these systems, right, and this is going to be true if you're building this yourself, you're going to help one team, and the next team is going to have you're going to do archaeological dig and find a new thing, and an archaeological dig to find the new thing. And that's normal. And it was a big deal for us to come back and say, we're not going to tell our customers they're wrong, and we're not going to tell our customers they need to drop a system. You have to take the systems as they are. And we ended up getting all those 10 integrations. We got the timing right, and we were able to deliver those bits and pieces. But we could not have done that if we had not realized and been ready for the fact that we had all these integrations and that was a normal part of the system. The next thing that happened to us was we actually had to make a very big change. So we'd been building this system without having written a real database. Now, you might say, all right, why don't you have a database? Our product is a first-in platform, meaning it is used when you bootstrap a data center with nothing else there. So having prerequisites, even something as simple as CoreSync or a database, is actually looked down on from our customers. They want to be able to start one thing and get everything else running. And that's been a requirement for us from a long time. There's another component to this, and the way we do infrastructure is code. There's a whole another hour lecture. But what we've been able to do by having our own database is it's layered, and the automation goes into locked layers that are immutable, and the state goes into a separate layer that is mutable, and commingling mutable and immutable artifacts is an incredibly powerful thing. But what happened was, as we grew into the 1,000-ish number of components, we started getting back into this locking problem that we'd had with Chef. Meaning we would write data in, and we started to notice that every write was starting to get locked against basically one object type. And once we saw that, we realized that we couldn't scale the current file system as was. We actually had to rewrite the file system into something that was threaded, that was able to do locking in a distributed way, was able to lock more granularly, fundamentally. And in doing that, we took what had been an open source product, and we're like, we're about to invest a huge amount of IP. We still continue to involve the back end for it. And we realized that we could not keep doing that as open source. And this wasn't a gentle nudge from us. We had customers, I should say prospects, sometimes we would call them freeloaders, who were using, and these are top name companies in the Valley, I won't name them, who would tell us, oh yeah, we want to drive your system to 10,000 machines. We need you to make these changes to your core database, but we will not pay you for it. The privilege of us using your software is enough. And that was not our goal in writing software. We're doing production support for people, and we write software that we collaboratively help run people's data centers, try and improve their lives like that. So we actually, in order to make all of those changes, we realized we had to take the system, and most of the product is still open source, but the proprietary pieces that actually run to 10,000 machine scale are RackN IP. And we don't apologize for that. We think that that was the right choice, and it enabled our customers to actually see more of our code, which they like. And that's where we're getting to with the 10,000 machine story. So we had to rewrite that back end. We had to go back through and deal with the locking issues and the file problems. And last year, we got into the case where our customers finally got ahead of us from a scale perspective. And it's worth explaining this, because this is one of those calls that sort of sucks to get. Y'all, I'm sure, right? We have, I'll tell the story a little slowly. So we have a banking customer. They're globally distributed. They have sites all over the world. And all their sites work great. Most of those sites are 1,000, 1,500, 2,000 machines, well under any scaling threshold that we would ever see. But they have one group, and that's the design. The part of what we've been able to do is the system is designed to be federated. So instead of expecting you to scale up, what we expect to happen is that you're going to take individual sites and have them be distributed local to where they need to go, or a team by team by team, and then you have a federated control plane where you can watch everything that's happening, and the scaling criteria for that is different because it's a mirror. But one of our customer sites they don't do that model. They like to have everything in one centralized database. As much as we tell them that's not a good idea, that's what they want to do, and that's fine. So they'd been growing up to 10,000 machines. Our engineers happily run tests at that scale to make sure the UI and the API and all that stuff happily, all the bits flip and things like that. So we were thinking things were pretty good until a Friday afternoon. And this customer, it's always Friday afternoon. Always, tickets always come in on Friday at 3. And so they had done an HA failover test. And they called us up and said, we're doing this HA test. Thank God it's a test. And the system's not coming back online. And we said, OK, what happened? Why isn't it coming back online? And they shipped us their logs. We replicated it. And it took us, on our systems, 2 hours for that system to come back online. What we realized was that even though we were handling 10,000 machines in the system just fine, the logs that we were generating where we trace what the jobs are, so everything we do transparent, remember transparency is super important for us, where everything we do comes back to a job log. And this site, because they had so many machines, had generated, I think it was over 10 million job logs. And the problem wasn't whether we could store 10 million job logs. It was the startup time of loading 10 million job logs. And we spent 3 or 4 months optimizing load times, adding pruning that didn't lock the database, all this stuff. The thing that still amazes me, because we had this big meeting at the end of this, and we're like, we're going to have to shard the database and do all this big work again. And it turned out that the problem was not the number of units, it was just this load time. And so we were able to fix the optimization of the system, not by fancy database tricks and multi-threading and concurrency and all that stuff, that's important, but by improving the pruning algorithms so those jobs didn't stick around when they weren't needed, and warning people that they needed to get pruned. And that actually pushed us over the 10,000 units for this customer without any problem. And it's important to think through, right? If you're in an HA scenario and you have a cold start on a system, you better make, that can't come up in 10 minutes. It has to be in a reasonable amount of time for those to come up. And so that was a huge changes. And one of the reasons why that happens for us is that objects are linked together and there's a whole bunch of denormalized data, and that's just the way things are. I'm going to leave a couple minutes for questions, but I do want to go through some of these lessons learned. Hopefully my stories illustrate these, so I'm not going to try and repeat too much. But this is a human scale problem, so don't over-design for a problem that you might have. Design for the problems you have and count on the fact that these are human scale systems to do it. Decentralizing and distributing work has been really important. I didn't talk about how important our API protections are. If you went back to our 3.0 days, so 5 years ago, the APIs that we have would still work. The commands in the CLI from that version of the product would still work on today's product 5 years later. We are ruthless at protecting APIs because it sucks to be an operator and make a call and have it not work because you've upgraded the back end of the server. I talked about transparency. One of the other lessons that we've learned that really improves scale is to fail quickly. Retries are really expensive, but more than that, retries hide operational deficiencies. And so one of the ways we help our customers scale is when something is wrong, the system stops. Right? If you're used to Chef or Puppet or something like that, and it just keeps retrying until it eventually succeeds, you are hiding operational problems that you need to fix. And one of the ways we help our customers scale is by exposing operational problems and then letting them fix the root cause of the problem rather than keep going. I talked about graphing. And then as code is super important. So in all of this, I haven't talked through so much just how much effort we put into this idea that I can version my automation, I can make it portable. There's so much we do in the design that is about how do I make sure a piece of code for us doesn't turn into Ansible Galaxy, where it's all forks and 20 people did the same thing 10 different ways, 30 different ways. And that's really important. This idea of immutability that everybody loves with Dockers and containers is a superpower. And if nothing else, when we look at how we build automation, the fact that you can have sites that are verifiably identical or different in known ways, and the count on immutability for that, it's super important on how things go. We want to talk to you about this. I'm trying to be fast and conserve time. We have a booth down here, and we're happy to talk about these lessons learned and how we do this and what we do. And we do this because we like to collaborate with operators and improve and constantly iterate over things. And we're hoping that you will participate with us in that journey. Thank you.